Right. Okay, good morning. So my presentation is on a pipeline inspection survey that we did in the Caspian Sea in collaboration with BP and Fugro Survey Caspian. And it actually follows up really nicely with what Kevin talked about as in the pipeline surveys and the challenges you have and how we use the new technologies to come up with good data and lots of data, really. What I'll be talking about today is I'll first go through some words about the setup and the installation, and then I'll go over the new technologies that we used. It's just a brief introduction. If you're following the workshops, you'll be getting more detailed information about these technologies as well. And then I'll continue with the results. So when you're looking at a pipeline survey, we're obviously looking for the pipe, but also lots of other objects. Think about pipeline crossings, a piggyback, sleepers, manifolds, mattresses that cover the pipe. So a lot of things to look at, and then also a lot of things to measure. So we're measuring the top of the pipe, free spans, the bathy around it, pipe burials, scouring, exposures, debris, all that. And all that kind of information is something you can get with multibeam sounder, whether you analyze the bathy or the backscatter. Maybe not so much the pipe burial, you probably use a pipe tracker for that. So when typically a multibeam survey, you'd use, for example, a side scan sonar. And with a side scan, you get a really nice image. So an example here, really nice defined image. I'm seeing lots of debris here. Can clearly see it. Can clearly see the pipe. The trouble is, of course, you just have two fat beams on either side, so you just have the two-way travel times, and your geometry is never as precise as, for example, with a multi-beam. So I can estimate, using these shadows, I can estimate the geometry of these objects and the free spans, but it's, of course, not as precise as you might want to. And then, of course, because I'm going on one side, just imaging this pipe from this side, I'd have to come back. So each pipeline, you need to run two lines. Another method would be, for example, using an ROV. So you can get closer to the pipe. You can use the multi-beam sonars. Speeds are much slower. And then one problem they had, particularly in the Caspian Sea, is where they have very poor visibility, especially at the shallow part up on the shelf break. So there was that, and then there's also that the state, Azerbaijan state, wouldn't really stimulate ship owners to bring their ships into the Caspian Sea. It's landlocked, first of all, so it's really hard to get DP vessels and ROVs in the Caspian Sea. So they were looking at another method, and this is then the alternative. So we have a vessel with two pole mounts and a 7125 at 15 degrees, imaging the pipe from both sides. And then those outfitted with flex mode, full rate dual-head, X-range, and then the pipe tracker. And we'd be operating this in relatively shallow water. So we went up to about 30-meter contour and surveyed about 700 kilometers of pipe there. So we'll be using a relatively cheap vessel then to outfit this, and then the BP was interested in the bathy, but also specifically in the backscatter. So just look at the setup. Normally, if you have a pole mount, you'd have relatively small vessels. You would have a pole mount. This being a large vessel, you need a large pole. And just to give you an idea of scale, this is the truck bringing the pole. It's a long pole. This is 9 meters, and then there's another meter on top of that for the extension to give that 15-degree angle. So it's the total pole length was 10.12 meters. Really large pole. We need that length because, well, we're pointing up, so we don't want to get any reflections from the hull. And because you have these large lever arms, you also have to bring the pole lower or bring the sonar lower. The danger is with these pole mounts is that you have a large part of the pole is unsupported, and then the pole might start to vibrate, and you'd see that in the data. So you want to keep that unsupported part as short as possible. So we have a large catcher that was welded on the hull, and you can see that here. So this is, they actually did is they listed the vessel to one side so they could weld this catcher as low as possible. So this is the whole catcher below the waterline when they're welding it, and this is when it's finished. So you can just see it come up. It actually turned out to be a really stable installation. We didn't have any issues with flexing or vibrations or such. So each pole was outfitted with a TSS motion sensor. So that if there would be any vibration or such, that would be captured in the TSS and corrected for that. Also, the motion data would be fed into the sonar head for the roll stabilization. So you have two sonar heads, both with their own TSS and both doing the roll stabilization. Then we had another pair of motion sensors on the vessel itself, and that was used to calculate the draft changes. So due to ballasting, the vessel will list slightly, and over the course of the whole survey, it will start to list a little bit. And it's not a lot, but because we have these large lever arms, you will start to notice it. If you have just your sonar at the keel, it wouldn't really be a problem. But with these large lever arms here, you would start to notice a difference in draft. So those are measured by using the octans and the Applanix IMU. So we use, and then in post-processing, the actual draft difference was calculated. So again, over a whole week, we just had a roll difference plus or minus half a degree, which isn't a lot, but lever arms of 8 meters will contribute to a difference in draft. You can see that here. So this is 7 days, and this is then the draft for each head. And so you have about 10 centimeters at each head, and that would actually lead up to 20 centimeters, in fact, in total draft difference. Okay, so far the installation. As I mentioned, I'll just quickly review a few of the technologies that we used, and again, we'll go more detail for the workshops today and tomorrow. So we're looking at the different way of distributing the beams, flex mode, using the FM pulse for X-range and full rate dual head, and using real-time pipe tracker. So using the flex mode, I guess in a standard situation, if you want to focus lots of your beams on one part of the swath, you might have to condense your swath and to get most of the beams in one part. In this case, a pipe that could be a wreck or a key wall or such. And then, of course, by doing that, you sacrifice your coverage. What you can do with flex mode is you can assign as a certain part of your swath as the high density zone and focus this on your target. So I'm still getting lots of beams, lots of hits on my pipe, and I can still get a general appreciation of the seabed. So would there be an object here or a seabed change here, I could still pick it up, but most of the detail, of course, is on the pipe. So here's an example where I'm running in a normal mode, then changing to flex mode. As soon as I start into flex mode, you can see these wedges here. They define the flex sector. And then I can change the outside beam spacing. And basically by changing the outside beam spacing, I'll fit in all the remaining beams in the flex zone. So that's what you will see then. That's going to change here. The outside beam spacing is changing. And you can see now I have less beams here in the outer edges, but most of the beams are condensed in this focus zone. You can change the width of your flex zone, and you can steer it. So again, this is stuff that we'll go through in the workshops, and you can play with this yourself. You get an idea of the spacing or the resolution that you can get. Okay. So this is an animation where we're going over a pipe. This is our flex zone. This is all point cloud data. It looks like as if this is one solid piece, but these are just really dense soundings altogether. Would there be an object here, you would still be able to pick it up. But of course, most of the beams are focused on your pipe in this case. You can see the field joints here, and you can see some sand build up on the sides. Okay. Another new feature that we used was X-range, and that was by implementing the FM pulse. Normally we'd be using a CW pulse, and with the CW you always have this trade-off between resolution and range. So where normally with a small pulse length would give you the best resolution but the poorest range, so that means that at some point if you're just surveying, you go into deeper water, you'd have to start cropping your swath because you're losing the outer beams. Simply because the range gets too large. FM, we have a larger pulse, so we have more energy, and therefore you can extend the range. And then in order to ensure the resolution, we're doing some clever stuff in the signal processing, so you have a better range performance and you hold the resolution. So in this case, where this would be my standard situation, this, let's say my energy envelope, at some point, to go into deeper depth, I would have to start cropping my swath with X-range because you have extended range. You can continue using that same swath angle, and meaning you get more coverage and spending less time on your survey. Alternatively, if you're in shallow water, you can now point up the banks, for example, shallow banks, which you otherwise wouldn't be able to reach. So that's then using the FM for X-range. This is collected during that survey in the Caspian Sea, and you're flipping between the CW and the FM pulse. So I'm now in 200 meters of water. I'm using 400 kilohertz. Normally you wouldn't use this type of frequency at these depths, but this was part of a different trial. So I'm now 200 meters of water. My cross-track distance is 225 meters. And well, that's my effective swath width. There's more stuff here on the sides, but that's not really good data. That's data you wouldn't be using because that's the limit of your range. So your effective swath width is really 225 meters, and this is using a CW pulse. So then it switches to the FM pulse, and then you can see the gain on each side, a much larger coverage, and then switching back to the CW. And then losing my coverage, and then back to FM. So from the same water depths, first I had 255 meters of cross track, and now I have 350 meters of cross track. So that's a big improvement, and it's just a switch in the software that you have to do. This, by the way, I was running in flex mode, so this is why you see this dark band here. That's all the beams being condensed in one part. So the other use of the FM pulse is for a full rate dual head. In your standard situation with the CW pulse, you'd have, we call this ping pong effect. So you'd have one head pings, and then the other head has to wait before one head finishes pinging or listening, receiving data, and then the other head can ping. So you have this ping pong effect. So your along track resolution is basically halved. You can only achieve that near nadir with these two swaths overlap. And but you skip a ping every time. And then by using full rate dual head, it can discriminate which echoes come from which sonar head. So you have that full, you actually have the same along track resolution across your whole swath. And that's something maybe the issue you were talking about of you going in F or CW mode or dual head and losing your ping rate, or yeah. Okay, then the last one was the pipe detection algorithm that we used. This is the algorithm that's embedded in PDS. It's also embedded now in the SeaBat user interface. what that does, analyzes all the data coming in and then finds the 5 points, it finds the top of pipe, the seabed just adjacent to the pipe, and the mean seabed. And it does that for each ping on the fly. So it will make it much easier to get this information rather than, for example, do it in post-processing or maybe even doing it manually. And it has then two really nice byproducts. One being the flex steering. So if I know where the pipe is, I can steer my flex zone to the pipe. So if the ROV or ship moves away from the pipe, I can always ensure that most of my beams are focused on the pipe. And the other nice byproduct is because I know what the shape of the pipe is, I can use that for my bottom detection, so the bottom detection is improved every time. So just looking into the results then, we surveyed for 7 days and we collected 710 kilometer data, pipeline data, so that's about 100 kilometers a day. We did the same survey a few weeks ago and similar results again. So the pipe diameters varied from 12 to 30 inch, mostly on the shallow waters. So that's the shelf break is around 30 to 50 meters. So that's where we're doing most of the work. And then we followed one pipe as an experiment up to 200 meters water depth. Okay, so I'll just give you a little animation of what the pipe detection looks like in PDS. Just have to exit this presentation for a second. There we go. In real time, the data comes in much quicker, but due to the resolution of this AVI, it looks a bit slower. What you're seeing, this is PDS. Then this is a background map with the pipes. Here's a ship coming in, and this is data from port and starboard side head. Then this is a 3D model of the vessel with the multibeam data, so both swaths showing it, and then it shows the detections from both heads, so green, red for port starboard. I'll just skip through it. So it's now coming back online, and we're starting to see a whole bunch of pipes within the swath. So PDS makes the pipe detections, and it does that for each swath, and then it connects all these pipe detections together to make a pipe route. And that's that purple pipe then. So it had done this line before, it just went back online, so that's why you're seeing this purple line here. That was the previous pipeline route that it detected. So again, here you can see both swaths from both heads, and then the detections from each head, making up the pipeline. Okay, then looking at some data. So this is the a 30-inch pipe at 17 meters water depth. This is my flex zone, and then here are the other soundings. I'm not sure if you can see that well on this screen, but so the swath extends beyond this flex zone, of course. Lots of hits on the pipe. I can't remember how many, but many hits, and then of course from both heads. So the beam footprint here is 15 centimeters, and then this is then what it looks like in PDS. So the PDS does the pipe detection and makes the pipeline route, draws up the route here, and here's an example of data from each head, port and starboard, and then this is the pipe that fits right in there. So you can see some sand buildup on this side, and it follows the pipe on this side. And then what we did, we compared the top of pipe data from the algorithm with top of pipe data from an ROV survey, and that's being displayed here. It matches up really nicely, and I think what's important to realize is that this is just a dump. So while you're collecting the data, it does all the calculations, the pipe detections, and then in the office you just do the dump out the data and bring it up. This is unedited, and there's no manual editing involved in here. And of course, the obvious advantage from an automated process is that it is an algorithm that does it. So normally, if you'd have different people interpreting the data, they would get different results. Here, whether you do it once or you run the algorithm 100 times, you always get the same results. So your workflow is more uniform. So now, slightly deeper water, 30 meters now. Footprint is 25 centimeters. And the pipe, again, you can find the pipe really well. And ROV and SV data matching up really well. So now we're in 40 meters of water. And this is kind of the maybe the limit of how far you would go. You can still clearly see the pipe. And again, the matches up really well compared with the RV data. So now we are in 100 meters of water depth, and of course the beam footprints get larger. But because we have that many soundings, you're still able to detect a pipe. Because of that large beam footprint, it is smeared a little bit, so it's more generalized. So the pipe is here. It detects both pipes, in fact. But of course, not as much definition, but that's just because your beam footprint gets that large. But we are at 100 meters, so still really good that it can detect it. So, like I said, we went up to 200 meters to test how far it went, and this is with the 400 kilohertz. Normally, you would be switching back to the 200 kilohertz at these depths. But just testing the algorithm, and well, there's the pipe again. Much noisier, of course, but I was still impressed that we could see the pipe at this frequency, at this depth. So some examples, some free spans. Some rock outcrops here, and the pipe is resting right on top of that. And those are the detections on the pipe. And these are the free spans calculated by the RV survey, from the RV survey. So again, where we have a free span calculated by the RV, we can see that, and really dense data. Here you can see the overlap of the two flex zones. So here's one, and here's one ending and the other one overlapping. What's interesting to see here is that the algorithm is expected to work really well on a flat seabed. Just a flat seabed, you have one pipe, you can easily detect that. But here you'd have the bedrock, and it's not confused by any objects on the seabed. It really locks onto the pipe itself. That's even more so in this example. So despite this not being in the flex zone, it just proves how robust the algorithm is, that it still detects the pipe. You would still want to have it in the flex zone, of course, because that's where you get most of the definition, and the pipeline engineers would really need that information. These are some sleepers. So they're large concrete structures that are used to help another pipe cross over. You can clearly find them in the data here. You can see scouring going around the sleepers, some sand build up here, and then the pipe crossing over it. So if you now look at this but then in the snippets data, really nice image, because I can see the sleepers here. First off, if anybody's familiar looking at backscatter, multibeam backscatter, you always see this nadir striping. So that always happens near nadir. In this case, because we have the sonar at an angle, it's slightly offset. So we have this nadir striping, and then it's imaging the pipe from this side. You can see a shadow behind it, and then clearly the sleepers, this pipe. So that's port side. Now look starboard side. Here I just had the shadow from one end, and then starboard side. You can see the data from the other image from the other side. Now, interesting thing to see is that right here there was another fiber optic cable, and it's been buried but exposed here, buried, then exposed, and then exposed here again until it's buried here and exposed here. And then look at this. So this is the snippets from port side, and then starboard side is, you can't really see it, but just by combining both images, you get that. So I'll just flip back and forth. You can see the difference. There's another small pipe or cable right here. Another interesting effect is that if you see the pipe here, it almost looks as if it goes into burial, but that's because there is in fact sand buildup on that side. And then looking at starboard side from the other end, you can see the pipe again. And then here's then the combined snippets backscatter. So a lot of information here just from the bathy and the backscatter as well. Okay. So a few conclusions we can take out of this project is that we used a new technology, but being able to accelerate the whole process, so we can get more data on the pipe. We don't need to use ROVs. I'm not saying we could still go back there with an ROV and use this more as a reconnaissance and then do an inspection from an ROV, but it saves a lot of time compared to ROV surveys, what they were normally doing in this area. So a different approach, but using the latest technology for that. As I mentioned, we did this project last year, and we just finished it a few weeks ago for a second time. So at this moment, I just want to thank the survey and ship crew from the Nefta Gas, and of course Fugro and BP for their involvement in this. And then from our side, Adam Jonner and Ashwin DeWilt, who took care of a lot of the data collection. Thank you.